Hey guys, so in this video I want to go over finding the transfer function for a circuit that includes resistors and now capacitors and inductors. So before with resistors it was very easy. All we had to use was our knowledge of KVL and KCL in order to figure out the V out to V in relationship. However, if we want to find the V out to V in relationship with these types of circuits, we'd have to start looking at differential equations. And that would be too tricky, right? Just imagine if there was more components here, like multiple capacitors, multiple inductors, the differential equations we'd be working with are absolutely insane. But we have a trick here. What we can do is we can treat both capacitors and inductors as complex impedances. And so by going from a time domain idea of differential equations to a frequency domain representation, we're able to actually create an algebraic expression to relate V out to V in. So long story short, no differential equations, we just have to use algebra. All right, so the first thing we need to do is we need to convert this circuit here into a complex impedance representation. And so Dr. Johnson, he likes to redraw the circuit, and for every component within the circuit, he likes to draw them as just boxes rather than their capacitor inductor symbol or inductor symbol, just so we remember that we're representing them as these complex impedances. So let's go ahead and do that. So we still have our source here, and it's still Vn. I'm going to say it's big Vn now. And now R, it's a complex of impedance, right? But resistors are not frequency dependent. So even though I'm drawing this as a complex impedance, its impedance is still just R. For the capacitor, we're also going to draw a box. But we know that as frequency increases across a capacitor, its impedance decreases. So we're going to say that its impedance is now 1 over CS. And the inductor is also going to turn into one of these complex impedance boxes. And since we know that inductors increase impedance as frequency increases, we know that its impedance is Ls. And now we're looking for big V out. Okay. So it's just a matter of, okay, let's condense this circuit like before using KVL and KCL. All right, so the first thing I notice is that this impedance box and this impedance box are in parallel. So let's go ahead and simplify that down. Redrawing V in. Got our R box here. Okay, and we're going to use the parallel rule. And we know from the parallel rule that this voltage and this voltage are the same, and when we combine them into a single component, it's still the same voltage. So we're just looking for this voltage here, which is still V out. Right, and we're going to use the parallel rule where we know it's 1 over CS times Ls all over the sum of 1 over CS plus Ls. And I'm going to simplify that down a little bit so we know that those S's go away. And I'm going to go ahead and multiply by CS on both top and bottom. So what is that? That's LCS over C all over 1 plus LCS squared. So let's keep simplifying. So that looks like it's going to be Ls over 1 plus LCS squared. Okay? And so then the next thing we notice is we have this resistive impedance in series with this resistive impedance. I'm going to solve for V out. So V out should be equal to Ls over 1 plus LCS squared all over R plus Ls all over 1 plus LCS squared times Vn. Okay, cool. Now we're able to relate input voltage to output voltage in the complex impedance domain. And so you would think here at this point we could just plug in our functions, right? V in and V out. So maybe like V in is like a sinusoid. You'd think I would just be able to plug in, okay, sine of t here, right? That doesn't work. Whenever you're dealing with the s variable, we're now in a complex type domain, and what we've really done is kind of a messy version of the Fourier transform. So once you get things in the complex impedance domain, it's not as simple as just plugging in values. You have to only plug in certain types of equations in order to figure out a proper input-output relationship. But anyway, I hope this video helped, and I'll see you guys in the next one.